Hello. So for those on YouTube, welcome to Paper Club from Emplan. Today we are going to discuss a very cool paper, which is very much focused on applications. So you will not see new ML methods here. Actually, we'll discuss that during the conversation about how they could use newer methods. But the idea is that this is, well, first of all, this paper attracted my attention because it had lots of really cool um, buzzwords. Things like generating text from images, segmentation from an image, using graphs to learn on urban structures. So it's a really cool application because they basically take images from social media, also from not sometimes, mostly just social media, uh, and then combine them in a clever way to build a knowledge graph representing a city. Okay, hopefully this is interesting, and we'll go over the details. Okay, Peter is here, so Peter, if anyone writes a message in the chat, please navigate that because I might not see it on my screen. Um, cool. So actually, let's scroll down to this nice diagram here describing what they do. Not here, even lower. This one, this is my favorite diagram because it really shows what the paper does. Okay, and then we'll go up and discuss the details. So this paper studies multimodal data, which means there are inputs from various sorts of data types, images, but also maps. So they use open source maps. The specific study here is for Chinese city, Wuhan. Um, and they also take images from social media and they combine everything. The point is, one of the inputs is a map, which has an image encoding into text. So we'll talk about this part, how it's a decoder. I guess you can call it this. It's a decoder because you generate a text description for each segmented part in the image using, well, and then you use BERT to convert the text into an embedding. So there is a bit of a long process here. I guess one question is why not embed the image directly, right? But anyway, here we also use the text to describe the image and its components. And then we use the maps that are taken from open source maps to build a graph representing neighborhoods in the city, right? So one thing is having embeddings describing cities. Another thing is describing neighborhoods in the city, right? And then this graph is now trained as a semi-supervised learning GNN because it's a massive city, you can only label a small part of it. And the labels represent city functions. So in here, they study about 10 types of functions, things like urban, hospital, green areas, and so on. We look at all 10 of those later. Okay, and then the goal is to detect rest of the city functions. And then once we have a description for each function and we have an accurate classification for each function, we'll talk about the accuracy later also. Then we can build a knowledge graph, which is also pretty cool because it also describes functions between different parts of the city. You can things like bus is parked at a urban area. Okay, we'll look at those examples later. So that's the knowledge graph part. Okay, any comments here about the overall point of the paper? Okay, The chat message. No, nothing new. Okay, so let's go into more details. I marked a few things here.
And if there's a chat message, I'll just unmute myself and tell you.
Cool, thanks. I have only one screen here, so I can't really see everything. Paper starts with an, I didn't mention one thing. At the end, they also study how the city changed, but basically taking maps from 10 years ago and from now and comparing them. There are a few other interesting studies about comparing the embeddings and so on, but I'll get to them later. So let's look at the first step. Okay, first step is we have an image, and then we find, we use RCNN, one of the standard image segmentations, the image segmentation algorithms, ML methods, to add labels on each image, right? We have collected these images of the city from social media open sources. And now you can see in these examples that we have, in these two images, we have things like a building, a tree, a window, skyscraper, and whatnot, right? Street lights and so on. So those are then taken out of the image. And as you can see, also as you can see here, we have the same area but from two different angles. And these are also mapped using their geolocations. So if you know that this is the same location, different angles, we also map those for the same area. And then let's see the other diagram here. Down here, there you go. So we use an LSTM to extract those features of segments in the image. So each segment in the image gets a feature vector. Okay, the LSTM part is fine because that's a standard method, right? And then they use this pre-trained vision language model, which takes image and generates a text. So they call it a decoder. On the right side here, there's the description of using two LSTMs, and then using this top-down attention mechanism between the segments to produce the text description. So here, this as an example, right? The image down here on the left would produce a text saying red car parked on the side of the road. Okay, so this is a pre-trained model using more generic image data set. There was one from Microsoft, they mentioned COCO, caption data set. So this is not specifically for cities. It's a more generic data set, but there is no city urban specific data set. So this one is good enough. Okay. Cool. Comments here? Right. And then once we have the text, we pass the text through BERT. There was a funny thing here because they mentioned BERT, but side the attention is all you need paper, very related, but not exactly the same. In any case, they use BERT to convert the text description into an embedding. There are some limitations as discussed at the end. For example, BERT can handle only 512 words, which is fairly limited. Newer, larger models can handle much larger text. So perhaps, and then they also discussed that sometimes text is a bit too long for BERT. So perhaps an easy extension improvement would be using a more modern language model, such as GPT, right? And then once we have the description, we can maybe go up here. And so this these produce these embeddings for each image. Now, each image gets multiple embeddings, right? Because we get an embedding for each segment in the image. This part gets a little bit confusing because the steps are long, but hopefully that's okay. And then what happens next is that we take the, let me find the GNN part. So obviously we have to use a GNN, right? Let's look here, this is fine. Because next, what happens next is that once we get the embeddings, now we have an embedding describing for each road, because those roads are given from the images. But then from a map, we also know that some roads intersect, right? So there must be correlations, because our goal is to detect city functions. So you can think of it, they give this example of a city function would be the whole paragraph, and each road in it would be a word, right? So we want to have a description, we want to have we want to classify the whole paragraph, the whole text. So here, we get embeddings for each road, but we also know that some roads are more related than others, which is where we use the maps to create a relationship graph. So this is an unweighted and unweighted graph without any. It's a very simple graph. Okay, no multi-graph, no directions on edges, no weights, no edge types, no edge features. We only have node features, which are the embeddings, each node in the graph represents a street. And then there are two ways that they cover here for building the graph. Maybe I can find down here. Let's see. No, there is no more. There is no image here. I'll just describe. There are two ways of building the graph. One is based on intersections. So if two roads intersect, then they are connected in the graph. The other thing is if they are geographically near each other, right? Two roads may be parallel, never intersect, but be very related. So based on their geographical location. So the other method maps those as connected. You can of course also do both, right? You can also have a denser graph combining both. Each case has advantages and disadvantages, obviously, and then they study which one works better. Actually, the method that looks at intersections seems to work better. But we'll look at the results later. Now, when we have a graph with features on each node representing a street, and our task is now to identify functions in the street. So we would be as subgraphs in the graph, the closely related subgraphs, which we can do by having labels on each node describing. So each label would describe one function. You can think of it as a multi-label classification problem, although they don't quite pose the problem as a multi-label classification. The way it's done here is that we basically do classification and take the most likely class as a class. And the important thing, the useful thing is that so the study graph here is from city of Wuhan, which has, I think they have more than 10,000 nodes. It's a very large graph, but not all nodes are labeled. They label only about 5% of the nodes, which is really encouraging, right? Because you don't want to, which means that you can get in other cities, you can label very few nodes and then assume that your model is able to generalize to other streets and other neighborhoods. Okay. And then they motivate why using a GNN, because naturally streets in the same neighborhood having the same function are related. So, which is what GNNs do, right? If you have two nodes connected to each other, the assumption is their nodes are similar, that their labels are also related. Any comments here? I went through the first steps on the GNNs. Cool. Those are the most technical parts. Here I made a little diagram for myself. How from an image, each segment with each is taken with its own embedding, passed through an LSTM, which is described up here, right? And then that ends up generating the text. Well, the question is, could we use a better text generation model, not an LSTM? Probably, right? But although the method side is actually quite new, so it's hard to say. Right. A few results here. So those are the types studied in the paper. Things like residential, business offices. Clearly, some of these are related, right? Might be difficult to differentiate between residential and business offices, for example, or educational. Which is why in previous studies, a few types have been considered. They mentioned two other studies. One of them had only 3 types, the other 6, I think. So they claim this is the first one that is able to classify 10 different types in the city. And notice that there is a huge class imbalance. So this is going to be a problem, right? If you have a fairly large class imbalance, some classes having only 24 instances, and the largest one having more than 1,000, this is going to be a problem. Which also means that the labeled numbers are also very few. You have only 6 labels, 6 types of transportation stations labeled. This is going to be very hard for the model to learn. We'll see later this, obviously. Right, then they describe the GNN. One thing I didn't like here is that they describe GNNs as our method, which is not fair, right? There is no new ML method introduced here. I would say the contribution of this paper is putting it all together for a very useful application. But motivating why the adjusting metrics in the GNN needs to be regularized and so on, this is not new. But basically, this is the one GNN layer, fairly standard. They discuss 3 types of GNNs, the GCN, GAT, and the graph sage. And the results we'll see later, but they do experiments with all 3 of them. And then they also have an interesting observation, which is having too many layers in the GNN can hurt. As a reminder, more layers means the current node gets messages passed from multiple hops, right? If you have 2 layers, you are using information from 2-hop neighborhood to learn a label for the current node. So obviously, if you have a too deep model, the messages get averaged out. And which is also what they observe here. Actually, they cite another study about geolocations, that having more than 2 layers usually hurts model performance, which is fairly common across applications of GNNs. Cool. They use a cross-entropy loss because it's a classification problem. And in the bottom here, we have the full 2-layer GNN description. So X here is the input features, which we extracted from the images. Okay, so basically for each street, we have a feature vector given in the X matrix. A hat is the modified adjacency matrix. Weights are W's are the learnable weights. So there are two layers. So we have W0, W1. There is a ReLU, and the last layer has a softmax for classification. Okay. And right. Any comments before I discuss the accuracy? Okay. So the model accuracy and prediction evaluation parts. This is interesting because they study multiple levels of accuracy. So they look at this P at K score, which basically means if you have, let's say, 80% at 1, it means that the accuracy is 80%. However, if you do 80% of 2, that means that because it's a graph, right? Some nodes are near the others. So if you have a 2, that means at least one of the nodes in the one hop neighborhood of the current node has the correct, has the predicted label, right? So depending on your graph density, this metric can be misleading. But on the other hand, because we are looking at functions, so subgraph classification, really, this may be a better score, right? So I was thinking it may make sense to come up with a better score for this kind of situations, but this is seems to be a standard one used in other papers. So they didn't propose this scoring method. So I guess that's fair. Okay, here we have an evaluation study of 12 models. They differ between BERT. Oh, they also study Dog2Vec instead of BERT, which is a fairly old language model, which isn't great at all. As actually as the experiment showed, this Dog2Vec doesn't work well at all. It barely learns, which actually you can see here. This other graph shows the learning curves, and as you can see, those flat lines are from Dog2Vec. So it's hard for the model to learn from those language embeddings. Dog2Vec is interesting method that's based on Word2Vec, which learns word embeddings, but also learns document embedding while training for word embeddings at the same time. So it's not averaging word embeddings in the text, but it does something more clever, but still not comparable to for foundation models, obviously. And then they also study a few models. GCN1, GCN2 is the number of layers, GATs, and GraphSage. Okay, as you can see, those numbers are not very encouraging, right? If you only look at the first level accuracy, this seems fairly low. However, that's probably okay, because if you look at the larger neighborhoods, accuracy is much better. Any comments here? I didn't mention those k-nearest and the Queen contingency weights. So basically, k-nearest looks at the nearest when we build the graph. As I said, we can use two different ways of building the graph. Right? K-nearest means we look at the nearest roads, and this Queen contingency is based on geographical locations. Okay, got some experiments, learning curves, and then based on these evaluations, they come to the conclusion that model 9 is the best, mostly because of here. So everything else follows is based on model 9. Okay. There are a few more studies here when they discuss a few more details about the method. So let's go look at them. So those are the t-SNE embeddings. The first one on the top left is the current method, and then the others cover using MLPs. They also study training an MLP instead of a GNN. And the conclusion is that MLPs learn much worse. But basically, again, it's difficult for an MLP to learn from those embeddings without taking into account the graph structures. Which kind of makes sense, right? Because we are really looking for labels for related streets. And here, as you can see, so this one I think is an MLP that can classify just 2 or 4 different classes. So classes that don't have enough labels don't get predicted at all. The good GNN, this is the model line, seems to do fairly well because similar classes are also near each other, right? This is what you would expect. Because Tisney is a dimension reduction clustering visualization tool. So you would expect the similar labels to be near each other here. Again, these other two methods also don't have the remaining labels, right? Cool. Here, this is as is expected, residentially. Many times, other types get classified as residential because residential has disproportionately large number of data points. Well, this last one is also interesting. So this not last. So this other one is predicting results of SOTA modeling. SOTA model is the model line in the study area. So here they use the model to predict areas, right? So those colors represent city functions, and then they put it on the map, right? So you can tell that those are residentials, this is that, that is that, and also comparing with the satellite images. I don't know the city well enough, but I claim that this is a very accurate representation. So you can see that labels are put on streets, and it makes sense, like because similar labels are near each other, which is a encouraging way to model the city. Oh, there was one interesting thing that I thought here. So one thing they do is they want to measure how close are embeddings from different functions, right? So if you take an embedding from embeddings from all residential streets, average them, and then do it for each different type, and then compute cosine distances between those averaged embeddings. They notice that those are often very similar. Actually, there is a graph here. So those are the similarities. Some of those are actually very similar, right? Residential and business are very similar. The furthest you get is like 80.8, somewhere here, 0.84. Then they are saying that this makes this means it's hard for the model to distinguish. However, I think there is a problem here, which is when you average embeddings, especially generated from a text, and then look at cosine similarities, there's a good chance everything gets smoothed and everything will be similar anyway, right? So the measuring distances between averaged embeddings may not be very representative. So perhaps it would make more sense to randomly sample embeddings from each neighborhood and then measure distance between those, and then maybe average the distances, right? Not compute distance between averaged embeddings, but average distances perhaps, because I think that's what's happening here. Any comments? No? Cool. The other thing is, well, they also show some randomly selected, not cherry-picked, randomly selected images from classified locations, which makes sense. So I is the green areas thing. So A is the residential, again, it makes sense. So those are the same area, but they put 4 images from the same area. So those are the same streets, actually. They randomly choose an example and a few images from that area, just to do a bit more of a demo. That's interesting. And the last part here is studying how the urban area changed, right? So this is the same city of Wuhan, and to measure how the city changed over time, they took an older map from, so the new one is from Tencent, the older one is from, forgot which one, from another map, which is older. And then they show on the map how the types changed, right? And then basically the conclusion is that green space is reduced, and the urban development increased over the last 10 years, which is consistent with what is known about the area anyway. So one thing that attracted me to this paper was the idea that they study how the city changes over time, which seemed really cool. But actually, it's not really how city changes over time, right? They're comparing 2 observations. It's not a continuous measure with multiple observations. That would be much better, I think. It would be really interesting to see like monthly updates or whatever is available. This is just 2 updates 10 years ago and last year. Okay. They also measure but show how the areas change. For example, residential, most of it remained the same, but some changed to industrial or commercial areas, right? And then you can also see that educational changed a lot, well, remained to educational, but changed to residential also. And you can basically look at these change tendencies and understand how your city is changing. I thought that's quite useful. Right. And this last one is also interesting. So this is the other buzzword, which is knowledge graphs. So after doing all this study, they build a knowledge graph for the city. So this is a little bit difficult to read. So there is a zoomed in version here, which really, the way they do it is using a language processing library that takes a sentence and then says which is a noun, which is a verb, which is an adjective in the sentence, right? So they took nouns as nodes. So bus or street would be the nodes, and the relationships would be given by the verbs or adjectives. So you would say bus is parked at a bus stop. Okay, bus is driving on a road. So this would represent the knowledge graph. So knowledge graph creation is done fairly automatically. So because you have the text that describes each neighborhood, which is generated by the text generation model discussed above. And then for those, actually for each street, we also get a knowledge graph, right? Describing the relationships. But you can also combine this with the actual map, with the graph that we studied before, to also represent neighborhoods in the knowledge graph. So this is a pretty extensive representation of the city. And then if you combine this also how it, I don't think they do that, but if you also combine this, how it changed compared to 10 years ago, you may also be able to study the changes, although maybe it's a bit too detailed, right? You can't really study how buses move, but you can study other sort of relationships, how they change. Okay, any comments here? I think that's all we have. In terms of conclusions, I found it quite interesting in the sense that many things are used. Now let me read the question.
So when it's posted, it would be interesting to compare knowledge graphs between cities. Are buses used differently in New York versus LA, and how that it might impact traffic?
Yeah, there are papers that do this sort of studies. It's a fairly active research area studying knowledge graphs, particularly for city dynamics. Yeah, that would be really cool. Right. In terms of the paper, I found the application very interesting because they apply so many different techniques, right? From images to text generation to learning on GNNs to building a knowledge graph. But there were a few slight disappointments, I'd say, because the language models are not the most recent ones. And the temporal part of changing graph is not exactly very recent, right? I think that's my conclusion. Any other comments? Cool. So this week we had a very application-focused paper. Soon we'll do Peter will do another one, which is very focused on language models, right, Peter?
I'm actually thinking of doing that after nerves, just so I can focus. Right. But
okay,
next
so
week I think I'm going to be. Oh, sorry.
Yeah.
I was just going to say next week I think I'm going to present this paper that just came out of Facebook called Segment Anything, and it's supposed to be a foundation model for segmentation. Like you could segment any image. They claim you can segment literally any image. So I think that could be a cool paper.
Yes, it was all over LinkedIn last week. Yeah, that would be a great paper to discuss. A bit more foundational, right? So we are looking forward to seeing you all next week. And thanks for coming.
Thanks, Vahan.